In this lecture, we're going to have a look at the notion of collision avoidance, which is specifically trying to detect if we think a collision is likely to happen. And it is the notion of prediction, that we want to imagine how we're moving, how other objects are moving, to look ahead and to say, okay, where are we going to be in the future? Where's the other objects going to be in the future? And if we suspect or we fear that a collision will happen if we carry on in our current trajectory and the other object does the same, then for us to take some corrective action. So it is a little bit more in terms of the planning phase. And we'll look at a couple of different ways whereby we can do this. It's important, or it can be important, to get this type of behavior into your game, because there are other forms of separating behavior, like we say with the steering behaviors, where you could remain separated from a bunch of objects. But sometimes we only want to separate if we fear a collision is going to happen. So if we have two objects which are moving in the same direction and quite close to one another, they won't hit because they're moving in the same direction. That may be the type of behavior that we're willing to accept, and it's only if we fear they're going to come together and collide at some point will we then try to move them apart or get one of them to take a change in its overall direction. So how do we do this then? We're going to look at a couple of different ways. One's going to be based on predicting future direction based on current velocity. The second one we'll give a brief overview of is the use of ray casting, when you're shooting out rays into the environment to try to detect if they're hitting anything. You need to take some appropriate action as a consequence. Now, when we detect a collision, we want to avoid it, so we'll use the evade behavior, we use the separate behavior. These are the types of ones that will trigger whenever a detection has been detected, or potential collision has been detected. Right, how do we do this then? Now, in principle, reasonably straightforward. You want to take two objects, you can see them here, object 1 and object 2. You want to, for sake of argument, because we'll be running this reasonably quickly, assume they're going to carry on with their current velocity. So it's a direction and a speed in that direction. And we want to ask just how close will those two objects get if they carry on along their current velocity. And you can see in the illustration we have over on the left-hand side that we're identifying a few illustrative points of closest approach. If you're doing this and you're projecting them forward, it isn't simply where the two lines cross over, because that doesn't take into account the speed of things. That if object 1 is moving very slowly and object 2 is moving very fast, then the object 2 is going to reach the intersection point when object 1 hasn't really gone very far at all. So we're interested in really working out, okay, take their velocities into account, take their positions into account, work out, if you like, the time, how far into the future we have to go when they are closest together, and then if we know that time, we can work out the distances they will be apart at that point in time. Now, how do we do this then? A little bit of maths is involved in doing this. It's not complicated maths, but it's useful nonetheless. It's going to be using a nice thing known as a dot product. So what we're assuming here is we have our two objects. Object 1's at position 1, object 2's at position 2. Object 1's moving with velocity 1, and object 2's moving with velocity 2. So far, so good. The equation that determines the time of closest approach, this is how far we have to step time forward, so to speak, until these two objects will be as close together as they're going to get, which may potentially be involving a collision, or it may just be, they're still apart, but this will tell us how close they do get. It is equal to, now, dp dot dv divided by the magnitude of dv squared. So let's just define what these terms are. So dp is the relative distance they are apart. So p1 minus p2. So almost as if I'm imagining that I'm p2 and I do p1 minus p2, this gives me, relative to me, whereabouts is the other object. That's how far it is away in terms of our initial times equal to 0. dv is relative velocity. So this is, in this case, v1 minus v2. So if I think about if I'm object 2 and I'm moving with a certain velocity, and I look over at the other object and I say, okay, relative to me, how is it moving? Is it going in exactly the same direction and exactly the same speed? In which case I will perceive it as not moving relative to me. It's going to maintain the same distance. Is it moving quickly towards me? In that case, its relative velocity is going to be quite fast towards me. Is it moving away from me? Its relative velocity then is going to be away. So they're the two pertinent things, and they make sense. How far apart the two objects are, and relative one to the other, how the two objects are moving in relation to one another. Are they getting closer? Are they staying the same velocity zero, so they're not moving, changing in terms of their position relative to one another, and so on. So we can work out dp, we can work out dv. The dot product is the thing then that combines these, and the dot product is actually a very easy thing to calculate. If we have two-dimensional vectors, x and y coordinates, you take the two x components, so you go to the p1 and p2, you take the x component of each of those, multiply them together. Then you take the y component of both of them, multiply them together. And then you add together those two things, that are the two multiplications. So x1 times x2 plus y1 times y2. If you had 3 dimensions, if there was a z factor, you would do exactly the same thing and all the way up. Now, dot products, very commonly used in a lot of areas of graphics programming. One of the nice things that they will do is they will tell us how correlated two vectors are. So if both vectors are more or less sort of heading in the same direction, so in that, what that would mean is that the distance we are apart, the velocity is moving such as to close that distance. Then we will have, relatively speaking, a large positive value being returned by x1 times x2 plus y1 times y2. If the two vectors are in opposite directions, so that would represent a case where we have a certain distance between them, but the relative velocity is acting to move the object away, so the relative distance is getting bigger. Then we will have a negative number coming out of our dot product. And if the two things are orthogonal, or right angles to one another, so this means I have a separating distance, but my velocity is such that that separating distance never changes, then my dot product is going to be 0. So it gives us a way of mapping one vector onto the other and working out how closely aligned the two things are. And we're going to use that then to work out if we're getting closer, if we're maintaining our distance, or if we're separating, moving apart. So dot product gives us this. Now the bottom line then, so dv, the lines around that is the magnitude then of dv. And if we're squaring it, then we're just taking the magnitude of the squared velocity, or the speed squared. Now, having plugged that in, we will then have time of closest approach. So this is how far notionally into the future we need to look until they're closest together. We can then plug those two things. So we know the current position, we know the velocity, we multiply that by the time, add that onto the current position. That will then give us the point in the future where they are closest together. We do that for both, we'll know the 2 points, and then we can calculate the distances from those 2 points. Little thing down there is mentioned that you actually can get a negative number coming out of this, so maybe a time of -2. What this means is that the objects are moving apart, that it would have been some point in the past when they were closest together. So if we get a negative time, it means the objects are separating, they're not closing. We don't need to worry about it in terms of collision avoidance. Now, if we use this here to get the 2 points, and we work out the 2 points, the distance in the future is sufficiently close for us to be worried about it, that we think, okay, there's going to be a collision, then we want to take some corrective action. The corrective action, it can differ a little bit, but generally speaking, we want to avoid or to evade the future location. So we don't avoid the current position of the object, rather we avoid where the collision is going to be in the future. And that will sort of give us smoother, more appropriate behavior. If we have multiple objects that we're moving around in the environment with, it's potential that we may be at risk of colliding with a number of them. That being the case, we would pick the time with the lowest value, if you like, the collision that's most imminent, and then avoid that one. There's a little aside here that there's a possibility, just in terms of the algorithms, that if they cross over exactly in the same spot, then we can't easily evade from that because it is going to be the same spot for both objects. So in that case, you would have some special behavior or action put in to change it around. So here we have sort of an algorithm that will help outline what that is. So we're passing in the source object and an array of other objects which we're assuming are moving around the environment, things that we want to avoid. We will remember the object that is closest to us in time, the one we're likely to collide with most soonly, or the soonest object. We will have a closest time, which will record, okay, for each object, just how far in the future we think we're at risk of hitting it. And initially we set that to a large positive value. So we're only going to reduce this as we find objects that we are going to collide with not too far in the future. So closest separation, closest distance, we'll use those variables. For determining the closest target, how do we do this? So this is effectively where we're using the algorithm that was set out on the last page, or the equation. So for each object in our targets, we work out its relative position, taking away the target position, source position, the relative velocity, so target velocity, source velocity. We then work out the relative speed, which is the length of the relative velocity, and the relative distance, which is the length of the vector representing the relative position one to another. So that gives us the speed, that gives us the distance, and we'll use those. The bit down here, the time to collide, this is where we are using the equation that was set out. So most MAS libraries, you'll find a dot product within that. You can pass in the two vectors. Alternatively, as mentioned, you're simply multiplying the two x components, the two y components together, and adding them for a two-dimensional vector. So you can write your own small method for doing that if need be. So we work out the dot product between the relative position, relative velocity, and we're dividing that by the relative speed squared, as you can see in the bottom line or bottom bit of that particular statement. We have a bit of testing then. So now that we find out the time to collide, we check to see what separation we will have at that point of closest approach. So there, the minimum separation is going to be the relative distance, the point they are, how far they are away at this point in time. Take away the relative speed times the time to collide. That will tell us just how close these two objects will get. The bit at the bottom then, the if statement, is where we check to see, okay, there's a bunch of objects we can sit in here in our targets array. Have we found one where we think, okay, this is imminent, we need to do something about it? So we check first of all if the minimum separation is less than the source radius and target radius. So we're assuming we have bounding circles around these objects. That's encapsulates the size of them, and that's what we'll use to work out, okay, so this point in time is how close they're going to be. At that point in time, are they going to be in collision, or are they still going to be apart? So we're going to check then our source and target radius to work out if a collision is going to happen, or if we can still carry on and we'll miss one another. So the first one says, the first bit of the if is that if they're going to collide, then the second if says if time to collide is greater than 0, in other words, it's something that's going to happen, and the time to collide is less than the closest time. So this is the one that we found that is going to happen soonest, sort of closest in time in the future. At that point, then we update and we remember the closest time, the closest target. So we're recording the one that is most imminent. Now, we'll do this for all objects, and then we'll check to see our closest target, do we have one? So if it's equal to null, what that means is that we looked through all objects and we didn't find any where if we look in the future directions, they're actually going to collide. So objects can carry on and they'll not collide. And that being the case, we just simply return. If we do have a closest target, it means there is something that we need to act upon, else a collision is imminent. That being the case, we're sort of doing close separation less than 0, so you've got a bit here to decide if you evade in your current position. We would do that if things are basically imminent and stuck up together, or if we evade in the future position. So this is something where we're looking ahead, based on the current motions. It'll be a collision if they carry on. At that point, we'll evade on the future locations. So not too much to this, and it actually is quite effective by way of enabling objects to avoid collisions as they move around within an environment. Now that works for moving objects, where different objects are going around. If we're thinking about static elements within our environment, so we may have large walls or buildings or things like that, we need to most probably use a different approach. So this comes into large objects and avoidance of large objects. So if you have walls, if you have other related ones, the bounding sphere thing we were using doesn't really apply. They're not necessarily going to have any velocity. So we need to look at a different approach in this particular instance. Different ways of doing it. One of the more capable, more common ways of doing it is ray casting. It's where we cast a ray out in front of the object at a certain distance, and we ask, if we cast this ray out, does it hit anything in the environment? And if that ray does hit something, we take the first thing that it hits, and we basically then have, normally you project out from the surface of the thing you're hitting, and that gives you a point that you'll seek towards or head towards, so you avoid hitting the other obstacle. And by doing that repeatedly, you can actually then sort of work your way around obstacles and carry on in your direction. May not always be nice and clean in terms of proper pathfinding, but generally speaking, it does okay for a lot of object shapes. You can see an example here. We have our object, the green triangle, casting the ray forward, where it's going to hit with a wall. And at the point of collision, we work out the normal, so which the normal to that surface pointing away from it, and we project out from the normal then our seek target, and we'll seek towards that, and that will help us then move along the wall until we get past it. For ray casting, a bit of pseudocode here. I'll sort of go through this here. I'm assuming there's a collision detector within this, so this is probably the most difficult bit of it. It's the thing that will take a ray and compare it against all of the things you have within the level. So it does depend if your level is based on a tile map or a collection of objects, or how you represent the objects within this. So this does differ specifically depending upon the game. But in essence, we're assuming our collision detector, you can give it a ray, and it will compare this against all of the objects we have within our game world and return any of them that we're going to collide with and tell us the normal to that. So a few things we have here: avoid distance and look ahead distance. So avoid distance is how far out from that object we will project if a collision is going to happen. So we try to stay close to it to try to move far away from it. The look ahead distance is how long each of these rays are going to be. Just how far out in front of ourselves do we look to see if we're going to hit something. And obviously you'll vary, and you'll select those depending upon the object size, the object speed, type of environment, and so on. We're creating an array. So array is just simply a vector. Initially we use the velocity of the object because that's the direction in which it's moving. We normalize that, so that gives us the direction, gets rid of the speed, and we scale it up by the look ahead distance. So there we will have a vector which is pointing in the direction of movement of the object, and the length is as how far ahead we want to look based on the length of the ray. We'll then go to our collision detector, and we'll say, okay, here's a vector as the current location of the object. Check to see if that collides with anything within the environment, and if it does, pick the one that you collide first with, or nearest to the object. We do this. If we get null from that, it means that we project the ray out, nothing gets hit, so there's nothing to worry about. In that case, we simply return, no action to be taken. Other than that, if we do have a collision, then we want to look at the normal thing pointing away from the object, to follow that normal by the avoid distance, and then that is what is going to be our target that we're then going to seek towards, and that will give us a way of avoiding that particular collision. There's a lot you can say about this. When you sort of skimming the surface, you get some sort of links on the screen there that you might want to have and explore off in terms of how you can sort of implement a number of these collision detection algorithms. Now, it can get fancy in terms of rays. Sometimes casting a single ray is not such a great thing. And you've got an example here over on the right hand side where you see a collision isn't being detected, that we have an object, a triangle, that is casting a single ray out from its center. And fair enough, the ray is avoiding the collision with the wall, but the outsides, the extents of the object are not, and it's going to clip it as it moves past it. So one single ray sometimes isn't enough. Different ways of getting around this. One is to use parallel side rays. So you go to the extents of the object and you cast rays, not from the center, but from either side of it. And that will avoid, for example, the situation we had here, but it's susceptible to what's known as the corner trap, though you can detect that and take some corrective action if need be. The corner trap is what is shown over here, is where you have two behaviors that cancel each other out. So the right hand ray is detected as a collision, and you would then be generating a seek which says turn to the right. The left hand ray is also into collision, where you'd be generating another seek target which says turn to the left. And that notion of turning to the right, turning to the left, both those things combined can potentially cancel one another out. In that case, it wouldn't turn either way and would simply plow straight into the wall. Different ways of doing this then. You can have one single ray projected out with a couple of smaller side whiskers, and they're used then if you get up close to the particular target. So that helps avoid a number of these things, but it's not good for small passages where the object wants to go down the middle of it. This will sort of bounce you from one side to the next. Another approach is to use two medium length whiskers going out. Again, there's less of a risk of a blind spot in this, not necessarily as good for a tight passage. So key takeaway is only really one in this. We looked at a couple of different approaches. Raycasting is quite a capable one in terms of enabling us to have an object that can move around within the environment to avoid walls or obstacles or other elements within it, and potentially other moving objects. If we're only interested in avoiding other moving objects, then we can use the collision avoidance technique, where we're predicting based on their future locations, their closest point of contact, and then evading if need be on that. They are quite capable mechanisms. They're useful ones to put in if it's particularly important within the game that we have obstacles or objects that move in a way where they do a reasonably good job of avoiding any potential collisions.